For this final project, we will be investigating magnetic resonance imaging, or more commonly known as an MRI, in addition to the physics principles that make this technology possible. Um, MRI is one of the most powerful imaging tools that is used in modern medicine. MRI scans allow doctors to see detailed images of organs, muscles, and soft tissues inside the body without having to do surgery. An MRI is most commonly used to diagnose conditions that affect the brain, joints, spine, and also the internal organs. One of the reasons that MRI is so valuable is that it does not use any ionizing radiation. Ionizing radiation is used in X-rays and CT scans. However, an MRI uses strong magnetic fields and radio waves to produce images. We will now begin reviewing basic physics concepts behind the MRI scanner. According to the textbook we have been using in class, University Physics Volume 2 from OpenStax, we were able to learn that magnetic resonance imaging is successful through studying the atomic nuclei behavior when they are placed in strong magnetic fields and exposed to radio frequency waves. Many atomic nuclei behave like tiny magnets. This is due to a property called spin. Spin is a quantum mechanical property of protons. Hydrogen atoms are very important for the MRI because a human body is made largely of water, and each water molecule contains two hydrogen atoms. The hydrogen nuclei contain one proton, and this proton behaves like a tiny magnet because of the spin property. When the body is placed inside the strong magnetic field of the MRI scanner, millions of these hydrogen nuclei align with the magnetic field. Because the hydrogen is so abundant throughout the body's tissues, these aligned nuclei create a strong detectable signal. When radio frequency waves are applied, the hydrogen nuclei briefly absorb energy and then are able to release that energy as they return to the alignment with the magnetic field. The MRI machine detects those signals going off and uses them to construct a very detailed image of the internal structures of the body. When a patient enters the MRI scanner, they are placed inside a very strong magnetic field. This field typically measures between 1.5 and 3 Tesla. To compare, the Earth's magnetic field is thousands of times weaker. Inside the MRI machine, the strong magnetic field, hydrogen nuclei begin to align either with or against the magnetic field. Next, the MRI machine sends radio frequency pulses into the body. These pulses temporarily disturb the alignment of those hydrogen nuclei. When the radio frequency pulse stops, the nuclei are able to relax back into that alignment with the magnetic field. As they do this, they release small electromagnetic signals. Once again, according to the OpenStax physics textbook, this process is called nuclear magnetic resonance. Sensors inside the MRI scanner detect the signals released by the hydrogen nuclei. A computer analyzes those signals and determines where they originated from inside the body. Because different tissues release different signals at different rates, the computer is able to reconstruct a cross-sectional image of internal structures with great detail. Research described in a review article available through the National Institutes of Health PubMed Central Database explains that an MRI is especially useful because it provides extremely high contrast between different types of soft tissue. The next section goes into iterating MRI safety and pregnancy. MRI imaging uses those magnetic fields and the radio frequency energy rather than ionizing radiation. The ionizing radiation is used in X-rays and CT scans, which damage DNA and potentially increase the risk of cancer when exposure is repeated. Because MRI relies on magnets rather than radiation, it is generally considered safer for repeated imaging. MRI is also sometimes used during pregnancy when doctors need detailed images and want to avoid exposing the fetus to radiation. This is another great factor as to why MRI is a very valuable imaging option when clinicians need detailed information alongside minimizing that radiation exposure. Thirdly, we will discuss specialized MRI applications. One interesting component of MRI scans that I found exploring MRI application is that specific scans can focus on specific organs. One example is a procedure called magnetic resonance cholangiopancreatography, or MRCP. This is a type of MRI scan that is used to examine the bile ducts, pancreas, and gallbladder. According to information published by the University Hospital Southampton in the United Kingdom, MRCP MRI scans sometimes may involve an interesting preparation step. The fun fact is that patients may be asked to drink pineapple juice before the scan. The reasoning behind this is that pineapple juice naturally contains compounds that suppress signals from fluids in the stomach and digestive tract. By reducing those signals, the MRI scanner can produce even clearer images of the bile ducts and pancreas. In this way, pineapple juice can actually act as a natural contrast agent, improving image quality in the MRCP scan without the need for stronger synthetic contrast materials. This example shows how imaging scientists and clinicians are able to continue to find creative ways to improve MRI image quality while keeping procedures safe and simple for patients. The following section is an analysis of the relevance of MRI technology to physics and society. The MRI scans are a great example of how discoveries in physics can actually lead to important medical technologies. The physical principles behind an MRI, including nuclear magnetic resonance, were first discovered by physicists studying atomic behavior in the 1940s. Two important scientists known as Felix Bloch and Edward Purcell, they investigated how atomic nuclei interacted with magnetic fields. At this time, when they were investigating their research, these discoveries were mainly important for physics and chemistry research. However, over time, more scientists were able to collaborate and realize that those same principles could actually be used to create images of the human body. Today, MRI plays a very critical role in diagnosing conditions such as brain tumors, strokes, spinal cord damage, ligament injuries, and cancer. MRI is particularly valuable because it produces extremely detailed images of the soft tissues, which these are often difficult to see using other imaging technologies. Researchers are continuing to improve MRI technology by developing stronger magnets, faster scanning techniques, and improving the image processing software. Some researchers are also developing portable MRI systems, which could make advanced imaging more accessible in rural or underserved areas. MRI demonstrates how advances in physics can directly improve healthcare, diagnosis, and patient outcomes. To further analyze, the key physics equation for an MRI scan is called the Larmor frequency. This describes how fast the hydrogen nuclei precess or rotate in a magnetic field. Uh, the equation is as follows: omega equals gamma b. In this equation, the omega represents the angular frequency of the proton's motion. Gamma is the gyromagnetic ratio, a constant for the hydrogen nuclei. B represents the strength of the magnetic field. That Larmor frequency equation shows that the frequency at which hydrogen nuclei rotate depends directly on the strength of the magnetic field. MRI machines are designed to send radio frequency pulses at exactly that frequency so the hydrogen nuclei absorb energy efficiently. That process is what is known as the resonance. According to the OpenStax physics textbook, when the radio frequency pulse matches the Larmor frequency, the hydrogen nuclei absorb energy and move out of the alignment with the magnetic field. When the pulse stops, they release that energy as electromagnetic signals, which is what is detected by the MRI scanner. The computer To conclude this review of magnetic resonance imaging, it is clear that MRI scans are a very powerful example of physics being applied to medicine. By utilizing the strong magnetic fields, radio frequency waves, and the behavior of hydrogen nuclei, MRI scanners can create the very detailed images of the body without needing to use harmful radiation or surgery. MRI technology also shows how discoveries in physics can lead to innovations that improve treatment, patient safety, and medical diagnostics. The following sources were used as references for this review on MRI technology. Number 1, OpenStax University Physics Volume 2, Rice University. Number 2, National Institutes of Health PubMed Central article on MRI imaging technology. The URL is https://pmc.nlm.nih.gov/articles/PMC4632105/. Source number 3, University Hospital Southampton, NHS Foundation Trust, Magnetic Resonance Cholangiopancreatography, parenthesis, MRCP, close parenthesis, patient information.